Nonlinear regression analysis with Navure. To illustrate this case of nonlinear regression, we will use a test data named growing_ducks, which contains the weights of 7 animals weighed weekly for 13 weeks. Each animal was weighed 3 times at each evaluation. The goal was to describe the weight growth curve of these animals. Locate this file in the test data repository. Preliminary examination of the data using a dot plot of weights versus week showed a nonlinear increase in weight over the weeks. To fit a general growth curve, we will use a nonlinear regression model. To proceed, press the Nonlinear Regression button on the Univariate tab of the ribbon bar. In the window that appears, we select weight as the response variable and week as the covariate and press the blue arrow button in the upper left corner of the window. A new dialog box appears with week already selected in the list of covariates. You can write the model in the Model Specification panel, or you can choose from several predefined nonlinear regression models that are displayed when you click the arrow at the right edge of the box, just below the model specification title. As you can see, there are several models to choose from. Therefore, you need to know which model is appropriate for your data. As we saw in our previous graphical exploration, the model should describe a sigmoidal curve. There are several models that describe such behavior. In this list, only the logistic and Gompertz models and 2 of their variants are available. For this example, we will fit a logistic model. When you select logistic, a formula is displayed in the panel below. It contains 3 parameters that characterize the logistic model: alpha, beta, and gamma. The formula includes the covariate week and the exponential function. Providing the algorithm with plausible starting values for the parameters is a very important issue when fitting nonlinear models. Depending on the initial values, the algorithm may converge on an unsatisfactory model or not converge at all. These values are displayed in the Starting Values for Parameters panel at the bottom of the window. They are automatically generated by a guessing algorithm but can be edited by the user. By default, if the model has a unique covariate, the algorithm will include a plot of the fitted curve. If you want to add the observed data points to the plot, you can select Observation in the Output Graphic options. To continue, press the OK button at the bottom right of the form. You will receive an analytical and a graphical output. The most important part of the analytical results are the estimated parameters, which are displayed in a table titled Fixed Effects Coefficients. The graphical output can be found in the Graphs tab. As mentioned in the introduction, the observations belong to 7 animals, each measured weekly for 13 weeks. This means that the observations are not independent. Independence is a key assumption of the estimation method we use to fit the model. A classic way to deal with this lack of independence is to include the effects of the ducks. However, the ducks are a contingency of the experiment. Their individual effect is not of interest at all. Therefore, we will include them as random effects. Let's go to the nonlinear procedure, again pressing the Nonlinear Regression button on the Univariate tab of the ribbon bar. Now we add duck to the Random Effects panel of the emerging window and press the blue arrow button at the upper left corner of the window. In the new window that appears, everything is as we left it. Now we select the Random Terms tab, drag duck to the Random Effects list, and the Parameters list will be activated. We need to decide on which parameters the random effect will be applied. We can select all or only some of them. The first impulse is to select all, but experience will make you more conservative, because most of the time applying random effects to all parameters will cause the algorithm not to converge. Typically, for sigmoid curves, the random effect is applied to the parameter that represents the asymptotic value. In this case, alpha. To visualize the random effects on the model, we check in the output options to obtain the predicted curves. To continue, press the OK button at the bottom right of the form. You will see the analytical and graphical output. The main effect on the parameter estimates is mainly related to the standard errors, some of which increase, and others decrease. To visualize the predicted curves, including the effect of each duck on alpha, go to the graphical output. Here we see several curves. We will select all the predicted ones and give them a gray color. To do this, simply drag the mouse with the left button pressed and select the 7 predicted curves. Then select the Series tab of the Graphic Optios group in the ribbon and choose the color from the Series Color Picker. This graph can be copied to the clipboard or exported in a variety of formats. Among these formats, you can use Scalable Vector Graphics, SVG, which allows you to edit it in other applications such as Microsoft PowerPoint.